Hello there, welcome to a problem session. Today we have an interesting question. It comes from IIT, Indian Institute of Technology, JEE exams, and I took it from 2021 test. I took it because it's a kind of numerical example of what we have been discussing, the concepts in AC circuits, except that I did not discuss the RMS voltage and current yet. So this includes this idea of RMS voltage and current, and you have an idea of power, impedance, phase, and phase of current related to source voltage. So if you're clear on all of these, this question is pretty simple actually. So let's look at let's look at this problem a little bit closely. Okay, so if you know how to do it, go ahead and try to do it. Otherwise you can see how I do it. So some definitions here, and I will really not show it, but RMS, let me write this down. RMS of a quantity is actually 1 over square root 2 of the amplitude. So RMS is this relationship. So if you have a voltage RMS and amplitude is V0, then it's going to be like this. So actual V may vary as a function of time. So like this could be the source. So here is the circuit. This circuit here, it looks like this. This is the lamp of resistance R. And then there is a capacitor of capacitance C in units of microfarad we're supposed to use. So this will be a source voltage which has a function like that. So this is called amplitude. And in here you will have current, sometimes to go that direction, sometimes to go in the other direction. So the current also depends on time. So if you write the current, as a function of time, so it's going to be like this, but this phase, it will vary with the same time, but the phase will be different, right? So this phase, so we have some amplitude, and you'll have a cosine omega t plus some phase phi, and we're supposed to find this also. That you're supposed to find that. So in terms of RMS for this current will be 1 over square root 2 related to this I0. So this is the RMS, and it's related to the amplitude of the oscillations. All right, where does this square root 2 come from? It comes from power. So when you look at the power at any time is say power through the resistor. Okay, so you have a current going through there and a voltage going through there. So if I have a resistor, so current is going through I of t, and between A and B across the resistor, voltage A minus B, and so voltage across the resistor is also a function of time. So but you know, they will have different, in terms of the phase of this is same as phase of that, we have explained. So this will be also some say VR, some voltage across here, but the current will be kind of like that, VR, cosine omega t, and it's going to have the same phase as that. So across the resistor, the power will be product of these two, I of t, VAB of t. Now when we say power, like when we say power in this kind of situations over here, this power here, somewhere this power here, that's average power. See, this is not a function of time, and power will be a function of time. So when somebody says something like power consumed by the lamp, they're meaning average power consumed by the lamp. So this is the, we want a time average. So so we'll have to do about, say, one time period of these oscillations, 0 to time period, and multiply these guys. So I have I0 V0 cosine square omega t plus phi. This actually adding phase doesn't make any difference. So if I do this integral out, you will find out it is 1/2 I0 V0. So if I want to write like IV, so what is the, you can see the relationship of VAB equals to, in terms of time, is IT times the resistor, and the cosine will cancel out. So VR, we kind of forgot R here, VR equals to VR equals to I0 R. So if I can write this whole thing in terms of I0 square over R, I can also write, let's see, times R, because I replace this with that, and then I can write the same way, V0 square over R. Now you can see that this whole thing, if I write as RMS square R, and this whole thing I write as VRMS square over R, then we have a IRMS square. Then this formula looks just like DC formulas, you know. So this is equal to 1/2 I0 square, and so that's the relationship. IRMS is 1/2 I0, and VRMS square is 1/2 VR square, and that's the relation for that RMS. So this for all the property that oscillate like this, and we define RMS that way. Okay, so now you know the definition of RMS. Let me kind of do this problem here. So okay, so let's read this. So this is the circuit. This is the circuit. Let me erase all of this, because these are all just definitions, and then we'll come back to it. Okay, so let's write down all the things we given. Okay, what's given is this RMS for this V, let's call it V0 RMS. So the source voltage RMS is 200 volt, and we will also need voltage drop across that. I'm just going to call VR RMS. Voltage across that is 100 volt. That's given, and the power used by RMS and time average, this I'm going to use the angle bracket to denote time average, is 500 watts, and we know this by formula is V R RMS square over R. So if I know the resistance, I mean, we know this guy, so we can, from here to here, you can get the resistance using this equation. So we know we can get, so let's get the resistance already. So resistance will be, this one is 100 volt, 100 times 100 is 500. So this is just a 20 ohm. So we know that this is 20 ohm. Just reading here, and supply here, omega is 2 pi f, and is 2 pi times 50 hertz. So this one will be this many radian per second. You know, in those unit, we just call it per second. But if you want to know, it's sometimes people write radian per second because it's going to be inside an angle like that. So that the whole angle is going to be in the radian if I use it omega. Okay, so we got that, we got that, we got that, we got that, and there's no L here, so we got that. We're now turn to circuit, and we know that these values are, this is RMS and this is RMS values. So actual, let's figure out the actual amplitude will be square root of 2 times 200 volt, and actual voltage in terms of the oscillating part will be square root 2 times 100 volt. Okay, so phi is in so the current I of t, it says current I of t, it should be written as cosine some I0 cosine this guy omega plus this phi. We've got this is in radian right now, then but the answer is supposed to be, this was supposed to be in degrees. So we'll convert this to degrees, to be converted to degrees. Right. And because there's a phase is needed, we're gonna need these guys. Maybe one of these we'll definitely need. Okay. So we suppose while C and phi. Let's see if I how would I get a phi? Well, first let's find C. How do I find a C? Well, we have a if we knew the impedance, if I knew the impedance of entire circuit, suppose this guy was, so it will become like 1Z. If I knew the impedance of this circuit, I would be able to get it very easily, right? So if I know the impedance of this circuit, the impedance of this circuit will be square root of R square, this guy, plus 1 over omega C square. So if I know this, so this is the amplitude, the complex impedance will also have some kind of phase, right? So I'm just looking at the amplitude part of this. So if I knew this, so if the way it will be related, so if this is V0 and the current going through is I0, so those are amplitudes. So I'm not looking at the phase part. So if we'll have a V0 will be equal to I0 Z0. So if I know how much current is going through, we already know this, so we can figure out Z, and then if we put Z here, we know already R, so this can be solved for C. That's my strategy, solving for C. Okay, let me erase a little bit. And so how I'm going to get, so I'm going to focus on doing I0 next, okay? So I'm going to get I0. Well, the current is going to flow here is the same current that's going to flow through this, right? So these are the same current. So if we're just going to be the resistor, we already know VR RMS, okay? And which is of course V0 over square root of 2, VR square root of 2. So this voltage is VR, and cosine omega t plus V. VR times this, so just looking at the amplitude part, and this is R. Then the current here will be I0 cosine omega t plus V times R is VR cosine omega t plus V. So you can see I could have worked with the RMS values. I'm just going to work with the amplitude values. These guys are all cancelled out. So I could have done square root 2 here, so this is RMS, and this square root 2, this is RMS. So we already know VR. Then so this is VRMS, this square root 2. So I0, IRMS, so this thing is IRMS, will be VRMS over R, and this VRMS is just 100. We can work just with RMS or with just amplitude because they're related by square root 2, so I don't really need to go back and forth. It's kind of wasting time during the test. R is equal to 20. So this is like a 5 amp. RMS is 5 amp. And of course, I0 is just going to be 5 is square root 2 amp. So they're related, so I'm not going to have to worry about one another. So now I've got I0. I got I0. I know Y is V0, so Z0. From there, I get a Z0 is equal to V0 over I0, and I0 is 5 square root of 2, and V0 is, this 200 square root 2. I could work with the RMS and the same deal, but because I have this relationship in the original circuit, I'm just going to work with that. So this is 40 ohm. Okay. So now if I put 40 inside here and try to solve for C, let me see what I get. I'm going to pause and okay, so let's find that out. And so we square it, so you have a Z0 square equals to R square plus 1 over omega C square, and so this minus equal to that, and so take that out, square root. So 1 over square root of Z0 square minus R square equals omega C. So C equals to times like that. Okay, so now we have 1 over, let's see, omega is 100 pi, and this is 40 square minus 20 square. So you can see here, so this is like a 4 square minus 2 square. So this is like 1 over 100 pi times 10 is square root of 16 minus 4. So this is square root of 12. So 1 over 1000 pi square root of 12 is 2 square root of 3 times pi, and this one they say is take that equal to 5. So this is with already included pi over here, so that becomes 10 to the power 10 1 2 3 4 minus 4. So it's actually this many farad. Kind of a little bit. So this becomes 10 to the power, it's 100 times 10 to the minus 6 farad. And so this will become 100 microfarad. Okay, I hope I didn't make some numerical error here. So I've done it earlier and I got a little bit different answer, so I don't know. Okay, let me pause and try to get phi. Okay, so I'm going to show you a couple of ways you can get phi. One is a kind of little clever way, and you have to know some physics, right? Guess around. So it's based on the idea that the voltage from here, some dropped here and some dropped here, but the phases here is different than phases here. So if you remember these things, like you have A and B and this R, then this VR and the current I through here, they have the same phase. Okay, so if VR of t is equal to some V0 cosine omega t, then IR of t is some I0 cosine omega t, same phase. But if you have a capacitor, so you have a and B, so across here is say VC and the current is ICT, then VC of t is a V0 cosine omega t, then IC of t is equal to V0 cosine omega t plus pi over 2. So like if you draw a diagram, actually this minus, it's minus, yeah, I will lead, yeah, I'm sorry, this is plus, yeah, plus minus signs in my head, I'm working it out. So this is the complex plane. So this is the, you can draw what are called phasors. We've talked about that in an earlier video. So if, say this was the current IR, then the voltage in the are in the same direction. But if you were to draw the voltage and phase relationship for the capacitors thing, so if this is the voltage across the capacitor, then the current is actually leads. Current is in that direction. So, but in this circuit is the same current going. So you can just for this circuit, you're gonna have some voltage drop across the resistor. Okay, so if this is phasor diagram, I'm gonna do a complex circuit. So here the current is the same. So you can say let's do the current in this direction. pick a time where the current is in that direction. So this is net current going that direction. IC and IR both. So this stands for I through R and I through C. It's the same current going through. Okay, these diagrams say that the resistor voltage will be in that direction. So let's see, you have a voltage drop across resistor in that way. And let's see, you have a voltage across the capacitor will be that way. And that should be equal to how much current you have. Okay. So if you look at the amplitude part only, I have a current, and then you are going to have a, instead of resistance, you're gonna use impedance for the capacitor. So this length of this arrow. Okay, so combination of these two is what the actual voltage of source. So the voltage of source should be this one, voltage of source. So that's this voltage, should be in that direction. So this is the angle we are looking for. So from here, phi is simply tangent of phi is whatever the VR is and whatever the VC is. So VR is just same as I0, I0 times R. So this is I0 times R, and this is V equals IR. No, this is just so this angle. So this is opposite, VC over VR. So I0 over omega C and I0R. So I can cancel this out, and this is 1 over omega RC. So that's the tangent phi. So tangent phi is VC, 1 over omega RC. So we already got all the values, and omega is 100 pi, and R was 20 ohms, and C was 10 to the power minus 4. So, so we need to just look at the calculator and see what the answer gets. So I'm going to look up the calculator. Probably I don't need to look up the calculator. See, they gave you that pi. So pi is 5 over square root of 3. So this is let me just see if I can. This will be 5 over square root of 3. So square root of 3, this is 5, that makes it 100. And so everything got cancelled out to 1. So this is square root of 3. And this, so phi is just turns out to be 60 degrees, right? So this is one way of doing this. And that's the answer. So you might say, what's another way of doing this, finding phi? And that's like you can just go out and do solve the whole thing in complex, okay? And so you can find it another way. Okay, the complex way. So complex way is we have this circuit and we convert them into boxes. So this remains R, and this becomes 1 over I omega C. So this turns into a Z, which is R plus 1 over I omega C. And this is my original V. So whatever the current is, so this is the V. So V equals to IZ. And V here, you write your V0, e to the power I omega t. And this I here is I0, e to the power I omega t plus V. And Z is Z0, e to the power I theta. So this you can write in complex. So from here you can see that we use V0 I0 Z0. That was one thing, and you need omega t cancelling out both sides. So you say phi equals to minus theta. So what's the theta? So Z is, this is Z. So we have R plus 1 over I omega C. So they'll write down over here. So R minus I 1 over omega C. So this is the real part and this is the imaginary part. So this is, you can see that this is the R and this is 1 over omega C. So this is that number, and so you can see that's going to be theta. So or you can so theta will be it's a negative number, so minus tangent theta, because going this way, 1 over omega C, and R. So theta will turn out to be minus 60 degrees, and you plug in here and that will give me plus 60 degrees. So this is a complex analysis way, and it's really cool, pretty nice. Now if you wanted to do Z0, you can get from here, thinking of this like that. So this distance, that's the Z0, and you can Z0 is just in this right angle triangle. Z0 is going to be just square equal to be R square plus 1 over omega C square. So in a previous video I said, once you go into the complex analysis, you really can do every single AC circuit problem very, very readily. So it's worth your while to learn how to do in a complex way. Okay, so I'm going to stop here. Just remind you to subscribe to this channel if you haven't done already. If you really like this kind of explanation, a detailed working out of things, I would appreciate if you can hit a like button. It helps the channel grow. Also, this is my textbook, and this textbook is also available open. It's an open source textbook series. Okay, so you can check this out. Take care. Bye bye.